plus and left eye. And we'll talk a bit about PET 3. We have to discuss FFPW and some of the libraries here we will not have time to discuss. So I will skip and hopefully just looking at this that gives you some idea where to look for numerical libraries if the things that we've discussed today does not fully unique. And just some slides for other numerical libraries. Okay, so on to BLAS. So what is BLAS? BLAS implements a low-level kernel to perform common linear algebra operations. So, for example, vector copy, vector scaling, if you just want to multiply a vector or multiply a vector with a scalar, and also do dot product, and you can do matrix vector multiplication, you can do matrix multiplication as you've seen. This is pretty much the de facto standard for linear algebra. So there will be many different emulations by many different vendors, but the interface, meaning the calling function or calling subroutine, pretty much use the same interface as the reference BLAS, because it's so common. So available implementation, for example, there's the reference implementation from Netlib, and Atlas is a version of BLAS when you compile it or when you configure it on your machine, do some kind of auto tuning to look for the best parameters or the best optimization for BLAS on your machines. And vendors also have different implementation of BLAS. For example, Intel has its own match kernel libraries, MKL, AMD has its own AMKL libraries, and Cray on Cray side that all implement BLAS with the same interface. BLAS is divided into what they call BLAS level 1, which is vector. So basically, the one is you add vector and you multiply the first vector with the scalar to get another vector. So it's a little bit of naming convention of BLAS here. The first letter is indicative of what kind of precision, what kind of real number you have. So S for single precision, B for double precision, C complex single precision, and Z for the double complex precision. So, for example, the routine DAXP, DAXPY would be for vector with double precision. And your vector supports 2 BLAS, and the common one is SGEM or DGEM, where you multiply a matrix with a vector, and of course on the left you have matrix multiplication, and DGEM is the common one. So I just put the 3 of the most common subroutine, but there are many more subroutines available from BLAS. So you should pick it up, and I'm sure if you do any kind of linear algebra with vector matrix BLAS profile, and it's for you to use. Just a quick example how we use DGEM and DGEM. So suppose we want to multiply a matrix and a vector. So matrix multiplication. The nice implementation would be you multiply each of the row of the vector with the row of the matrix and add that to the result. So this is kind of nested loop as nested loop here. And as I mentioned before, don't do this. Instead, you BLAS simply GEMP. The first asks whether or not you want to transpose your and just means no transpose, and this the first 2 arguments just give it the size of the matrix, number of row, number of column. if you do not want to multiply the matrix or the factor with any scalar, then you just give it 1. And the argument is the matrix itself. And it's what they call the leading dimension of the matrix. So in this case, if you allocate the memory of the matrix the same size of the matrix, then it's the n rows. But this gives the possibility that you allocate more of the matrix, but then you only want to pass a submatrix to the argument. So the n rows can be, or this argument can be bigger than the actual number of rows. But most of the time it's just similar, it's just the same number. And then the factor and the factor up. And the side and factor up can be inferred from the side. So this line or this 7 lines here is replaced by a positive line. Similarly, during matrix multiplication, this is implementation with nested loop as I have before. But in that, really what we do is called PGAM, which is the plus submatrix multiplication. And here you pass in also the size of the n, it's the size of the matrix A. K is of course the size, the dimension of your matrix P is the number of columns, and then you just pass in the matrix, and the result will be stored on matrix C. It's simple, but you just need to look, I guess, to this kind of call with a call to PGAM and PGAMV. So this level in plus, why is the level 1 equal to number 2? Oh, I have a typo here. So mainly for factor operations, and this is relational intensity and low data reading. Because there's only one, or I guess one program operation for each factor. So the computational intensity is low, and the speed is really limited by the memory bandwidth of the system. So every Q define the number of operations per memory reference. For level plus level 1, this is only 2 over Q. So for each 3, every time you pull from memory, you can only do 2 blocks. So there's not chance to really utilize all your processor capability. So matrix operation is a little bit better because there are more blocks from memory reference, and we do theoretical calculation. Q is equal to for level 2 matrix. To get to level 3, the matrix operation. Here we have the n cube operation on n squared data. So in principle, a lot more blocks. And Q is n over 2, where n is really the size of the matrix. So there are possibilities that you can really get almost close to the theoretical peak performance of your machine. So the problem here is, when possible at all, you should always cast your algorithm or cast your problem to use plus level 3, because you have a lot more utilization from your processor. So you need to solve multiple equations. You can sometimes in your algorithm development, you can maybe the simplest is to do matrix factor multiplication or matrix factor algorithm, where the factor is really the number of equations. But then if you need to solve many multiplications or many equations at a time, maybe it worth the time to change your algorithm so that you can have it in form of matrix. So there is a lot more flow. But level 1? Yes. So I guess the simple can imagine there's two at least to do vector. So you need to pull two. I can store another one. You store one with the vector out. It, well, flop is really multiple and add. Right? So you can multiple and add in one flop. So I'm a little bit hand waving here, but if you really go through the calculation, and then you can see, and I can see maybe later that it's two of the about comparison of the performance for plus with so really you want to see like you can. So kind of that is LabPack. It's linear algebra package. So LabPack do LabPack solve system of linear equations. Can also do a least square problem and do eigenvalue problem and singular value problem. And for its computation, LabPack use less level of phase. So this really uh, very efficient if your class is efficient, is implemented efficiently in your machine, LabPack can run efficiently as well. So it depends on the class implementation on your system. That's just an example of solve a general system of linear equations where x can be a pair, or if you have multiple equations, then x can be a matrix. Then in this case, you want to invert x is really what you want to solve. So you want to invert a in this case. So you call it here. This is the argument, really the list of arguments for GESP. So again, let's like this kind of similar convention for the name of the subroutine. So I've seen the number of linear equations, and this is n, really. And right hand side really just the number, your number of system number, the number of problems, yeah, we're n system. So A is the matrix, and LDA again is the leading dimension of the matrix. And PI3 is the pivot in this list. This is given to you by a LabPack from the decomposition. And V is really a vector, and LDP is the leading dimension of the array B. And gives you the info to indicate whether or not the solve was successful. So to solve this linear equation, really you just need to call DGESP, and this is all the argument that you need to pass in to LabPack. And then solve the plus computation. Pretty simple, you need to look it up. So this is kind of a functionality that LabPack provides. Obviously, we will not have time to go through all of this, but the linear system of equations and acronyms. So SP is linear for linear system of equations. You can also do least square problems, and all this is provided by LabPack. Will that recognize the basic advantage of the problem? Yes. Yes. So there are, so when you use DGESP, this is really for general metrics. But geometric appendix, for example, there okay, so you have to call it with the right substitution. It doesn't automatically figure it out. There's DGBSP, for example, where the matrix is pended, and if your matrix is has a different kind of structure, then there are different subroutines that you can call. Okay. You have to right. So I already have the area that you have already that level. Are you? R is routine that you can pass to do that, or you can. Now, I have to admit, I'm not an expert in this type of maybe not, but there is a way to pass in your facilitating already.
I was
Not with PGG, not with PGES. So you have to call it with routine.
I know for the PTSD
Again?
PTSD has several
Yeah.
what routine in the area.
When some
So you just keep the
output the early decomposition, you may be able to reconstruct it from the BlackBerry. Makes sense?
so okay.
Right.
You mean
Yes. That's right.
okay.
You can, yes, you can replace. Oh yeah, I hear your question. Yes, you just replace it with another.
Okay.
And so it's really large number of apparatus substituting the issue parallel plus and left side. So there are called class, which is implement level 2 and level 3 class, what is repeated in SQL designed for heterogeneous computing. There are other libraries, for example, Pepsi, which we will talk about next, that uses BLAS to implement parallel linear algebra. And so I will not talk about P plus and scale effect, but I'm going to introduce you a bit on Pepsi, this a more general implementation for software and linear algebra, and also handle sparse messages. So here on BLAS, LabHack, and NPR to do parallel linear algebra and other So basically a parallel toolkit to solve partial differential equations. But this goes more than just the dense linear algebra that's provided by LabHack. Provide common PD data structures as parallel vector and parallel matrix, which is available, for example, to use the BLAS and LabHack. And for example, parallel solve for linear system of equations. This kind of thing. You can do also solve for non-linear system of equations. And time stepping. It has utilities for debugging and profiling and logging, and it has many interfaces. So this is on most active resources and available, of course, on our website. Just talk parallel vector and parallel matrix, and then we'll take a quick example on the solution for linear system. If you want to use Pepsi, if your vectors and matrices are so big that it has to be distributed. This is the case where one compute node cannot hold all the elements because you have a memory limitation. And it's the case when, for example, one of your nodes can solve your question because you have computing. In this case, you have to distribute your vectors and matrices. Most of the time, I think the memory limitation is what people come up against when doing large linear algebra. So you have your domain already decomposed across multiple processes. So and processes contribute to different parts of the matrix. So if you already need domain decomposition, and probably it's conceivable for your particular solve that you can solve it on one node. You don't necessarily want to collect everything to one node to do a solution and distribute again. So one way to this is that everybody already has parts of the matrices and the vectors. Then let's just use distributed solve on the algebra. So we have extension the user can apply their own code, and this is necessary for callback. it can couple with different packages. So under the hood, PETSI use hyper and mom and parameters as an interface to all of them. So some of this is really next generation thing. So here we look at the structure of PETSI. The lowest level is the computational and communication kernel, which is MPI, MPLS, and LibApp. It has a profile interface and it has data structure, formatics, and factors and indices. There's some kind of grid management, so actually you can decode your problem using PETSI. And there it has the built-in linear solver and non-linear solver, and also has ODE interface. So to look at the numerical component of PETSI. So this is very large numerical library, and have to install too. Okay. Hello world from PETSI. So you do MPI in it, and you print a hello world, and if you run this, all processes will print hello world from MPI. Similar, if you do similar thing with PETSI, where the MPI init, you do PETSI initialize. So under the hood is the MPI init, and you can use PETSI print and case only the rank 0 right in PETSI. So it's kind of nice for debugging that you can get into the output. And you can also change the rank you want to print. PETSI factors. You can have sequential factors where there is a local copy of this processor, or you can have parallel factors where letters are across all processors. So function for each of these is different. The parallel created create NPI. In this case, for example, this factor, some of the factors is stored in processor 0 and some part in processor 1, etc. So factor to build solution left-hand side, and third, locally on a subfactor of contiguously numbered global entities. So contiguously numbered indices here by processor 0. You can ask PETSI to decide either the global size or the local size. So in this case, you can tell that I want the local size to be X, and PETSI will figure out the global size of the physical size. So here's an example. To create pretty simple, just to create, and you give it the communication context. In this case, it's PETSI convert, similar to MPI convert, but really you should use PETSI convert because PETSI has its own communication context. And here I decide the local and the PETSI decide will tell what the global size of the factor. And from option, really just take a command line option. So this is another nice thing from PETSI. You can set different command line and PETSI reads that. And set value, set the value. In this case, you want if you can do either insert value or add value, and meaning is obvious. And before the factor, you have to do fact assembly begin. And then if PETSI communicate or it will do to construct the factor across multiple, and fact assembly begin. In principle, you can do other things. So here where you want to, this is where you overlap communication and computation. So you can compute things or create the factors, and before you use it, then you have a fact assembly end to make sure that the factors are correctly distributed. And here also the example of that you can duplicate factors X to and you factor B. So factor operation on PETSI. So you can do X, right? It should be primary revision of the BLAS interface by vector AYPX, and also things you can do vector scale, copy, and get the norm, just very similar to the BLAS interface. Also, Petri altering and not really fine with BLAS, but also have there's also Petri matrices where you have matrix distributed across different processes. In Power Matrix, its process has some local contiguous role, and method type with the root access using the same interface. So this is a polymorphism in Petri. And the interface for, if you're familiar with the sparse matrix format, there is the same of matrix AIJ, block AIJ, and you can change that if you want to. And if what you're doing, for example, some format is better than others, but most of the time you can just use the default as a approximation. So we usually use to store the linear operators, and this is usually the coefficient of the discretized PDE operators. And this vector to create Petri matrix is four steps. Matrix first created, allocated, and then set the value. All processes can set the value here, and then you compute and communicate the value, and then when communication finished, you can use the actually multiple nodes. So this is a collective operation. Everyone calls matrix. It's a local copy of parts of the matrix. An example. So I want to store the matrix for 1D Laplacian operator or 2-point potential 1D Laplacian operator. So the matrix looks like this. So this is the trivalent matrix. So everyone called mat set sizes. In this, I choose the global size of the matrix. So whatever this n by n, or n by n in this case of the square matrix, and I Petri decide. So I let Petri decide how it will allocate matrix across all the processes. So we might set option to get the command line. Here, go through the loop to set the values. When at all possible, you should set more than one value. And so here I call mat set values for different number of rows. I set all the values. I say assembly begin. You know that now I can start communicating the matrix and distribute the number however it wants to. And in between there, I can do other things while waiting for the matrix to be communicated. And while I use the matrix, I say mat assembly end. And I call the matrix is ready. So if mat assembly begin immediately followed by mat assembly ends, then your code may block for a little bit to wait for the communication. So it's really best if you can do everything. So that maybe processor 0 will have this the matrix, processor 1 has this local part. So there are just some selected Petri matrix function. AXXP where, for example, do matrix multiply, matrix vector multiply, and there's mat mode to matrix multiply, and you can get the norm and the transpose and all that thing, very similar to what you will see in BLAS. statistically distributed method. So, a quick how we use the linear solver on X. So, can solve the linear in the form of AX in B. So really X is your solution, B is usually boundary condition, and A would be the operator. And KFP is in PETI, this is the abstract object that provides the common interface to many built-in subspace networks. So it provides many built-in options for different preconditioners. So use different methods and different preconditioners at runtime using a command line argument, or you can set it per application. You can set it in the calling function. So the next thing here is that you can quickly run with different kind of preconditioner, different kind of methods without actually changing your code and see what is the best solution, what is the best way to convert or the least error tolerance and that. So it's really good for you to experiment with different solutions. So here's a sample of the KSP methods available in PETI. Again, you can pick this with changing different command lines. So it's really nice if you have a lot of linear algebra calculations. So I'm not a mathematician, so I'm really not familiar with I don't know all of this on top of my head. So but there's a really good book that describes all these methods to do iterative solution for linear systems. So here is just an example of how we use KSP. So suppose we have the vectors X and B, and we have the matrix A, and KSP is really our object, the context. We create KSP with and we pass in the variable that we want to use to hold it. We set the operators, and we say different non-zero pattern because we don't have specific zero pattern. We set tolerance. This is KSP set from options to you can read from command line if you want to try to change with the method. And which is called KSP solve. We give it the right hand side and give it the solutions, and this will give you back the result of your computation. So the operators here is one of the important things. Operators give you the operators of the problem. So in our cases, you have one operator that of many or the same equation with different boundary conditions multiple times. So really, most of the time you just set the operator 1 and you change value of B and call KSP solve multiple times with different B factors. So in the case of B would change over time, and then you just call KSP solve X change time, and you just call set operators for every time because this is the expensive part of the setup. When it comes to KSP, there are many types of preconditioners you can try, and set from optional, you can change different methods and different preconditioners, and possible option is this is what you can pass from command line, just have this method, and you can pass different preconditioner type, and can say what is the maximum operation you want to wait for, and the tolerance, and so it has a very thorough documentation on the website. It also has different mailing list if you need to ask questions, and so these are the kind of resources you can use to some example that I will not go through. So example how to solve X plus B with the Laplacian. This is the solution that the analytical solution that we get. Go through the example, and I'll post this on the web later. There's also some code that go through the example. Then you should get from Betsy. Then you should be able to solve from parallel and get your analytical solution. The numerical solution that's very close to the analytical solution. So you can yourself at home for fun. So the last I have about FFTW. So what is FFTW? FFTW is Fourier transform and stands for the fastest Fourier transform in the universe. So what is it? Fourier transform is a mathematical transform that takes a function, for example, in time domain to its Fourier space, it is in frequency domain, and decompose signals into a set of frequencies that build the signal. So this is really used in signal processing and even in solving of PDE. So in computing, the continuous Fourier transform becomes the discrete Fourier transform. And definition of the discrete Fourier transform requires acute operation. The fast Fourier transform is a algorithm to compute the discrete Fourier transform that has n log n operation. So it's obviously much better than n square operation. So I have a library implementing a variety of FFTW. So FFTW can adapt to particular hardware, compiler, and program size by using an optimized plan and runtime. So during runtime, it will look for configuration or the best optimization that you can come up with, and come up with if you are related with a plan. It is actually called plan can use to compute your Fourier transform. So installation is pretty standard if you're familiar with any software installation. Fourier transform is for signal analysis, signal filtering. You can, for example, from a signal to a space, and by doing that, you know the condition that builds the signal, and that allows you to filter, for example, the higher frequency part or the low frequency part. And then you, after you take that out, you transform the real space. So useful in solving PDE and control, for example. It's useful in polynomial multiplication, so it's been used in areas like description. And data, if you're familiar with how it works, for example, all of that is based on Fourier transform and Fourier analysis. An example of how you do 1D complex transform in or using FFTW. So the aim is if you allocate a variable and you tell it the size of the number of elements you want to have in your input signal, and output the output signal, and you allocate with FFTW malloc. Not just use regular C malloc. Well, FFTW malloc knows more. Yes, is the short answer. It really pads and optimizes the memorization so that FFTW can utilize or perform best. So use FFTW malloc, and it's compatible with the C malloc. So I specify your input and output. You plan DFT1D is to do a 1D complex transform, and give it the forward. FFTW estimate tells you what kind of optimization you want FFTW to do. and calculated the different flags here. So I'll just list this right now. And after you plan, you populate your array in this case, and then we just do execute, and after execute, the array out will be the of the transform. So in this case, you only create the plan once because creating a plan is expensive. So most of the time, you create a plan one and you change the in and you execute multiple times. Once you write the plan to free up the memory, and FFPW free to free out the memory allocated by FFPW. So again, this is also important. The very similar C, but in this case, you have to use the Fortran 2003 standard for C binding for C interoperability. So the difference here is that in execute, there's a new routine FFPW execute DFC as an argument of the plan, the in, and the out. This is different from the C counterpart. The reason here that it's function of your alias and that sort of thing. So they just use FFPW execute plan. The compiler may say, well, the in and out is not changed and can optimize the way, and therefore does not actually right thing or change the order of in and out. So the FFPW has to come up with a different phase where in out is an argument of the interface to make sure that the compiler optimization before time does the correct thing. On the plan we talk about. So that the fastest algorithm given a specific problem on a specific hardware and set this plan. Or as an opaque data structure, the FFPW plan is related to the type and used for execution of transform. So then actual plans, and they call it the wisdom part, and we use it later. So, but you have to be careful when you're reusing wisdom from different systems. So, then accumulate plans for different problem size, for example, in the wisdom part. So, in creating the plan, we use estimate. This is a simple heuristic to pick a plan quickly, but you can also use measures which is more FFPW does more things to measure different execution times. It depends on how exhaustive you want this to be. You can go to your flag. So for FFPW, exhaustive would be in a larger number of algorithms to find the optimized algorithm to use on a specific thing. So this may not save you as much, but it takes a long time. So there's a setup you want to do here. But then if you want to do a lot of transform with the same plan, then it may work if you want exhaustive creating the plan and then you execute it multiple times. So a flag will be wisdom only. With if you combine it, you can either use the wisdom. So FFPW has the capability to look at whether you already have a plan for a specific problem, and if that's not the case, then you create a new plan. So let's look at the your wisdom part. Okay, you can also do multidimensional transform with a very similar interface. The interface for 2D and 3D transform. So multidimensional transform basically has similar as 1D, and it's basically just a sequence of 1D transform in each dimension. So really, a 3D transform is just forming X and Y and then polar in Z. Let's see. You will do multiple transform at one, then what you want to do is a plan of many DSP. So this is more efficient than calling the one depends on multiple times, because the FFPW has more than to even optimize the transform. So this is the kind of interface that FFPW has, and where how many is the number of transform, the input output IO embed is the size of the input output of the array, and you pass in the stripe, and you can also pass in the location of the K transform out of how many. So really, this is not this is the stripe of the array. This is the stripe of the transform. So this is then a loop over a single transform. So at the when you use, so malloc pre-allocate and pre-dynamic array so that it's in the line, the result to better speed up. So this is complicated in Fortran, but it can be done with an interoperability standard in C. And if you have, so indeed, there is no real support for multi-dimensional array. So most of the time, you want to do multi-dimensional array, what you can do is you do an array of pointers of an array. So don't do this in FFPW, because that's very incompatible with how FFPW see a memory. So just keep that in mind. It also has a multi-threading interface. Do that using POSIX threads or OpenMP. But you really need to figure enough problems to work it, otherwise you just lose the time in the thread synchronization. So FFPW also has a distributed memory with NPI, which we cover here. Cool interface, they export a lot more flexibility for transform, and I recommend using FFPW interface. Okay, so this idea, since this was part of our tutorial, and I get that code on the web. Just the last 2-3 minutes here, talk about the different vendor libraries for Flash and Latex. So most of you want to use an machine, and most of the time the machine or your resource provider will have recommendation of what kind or what is the best libraries to implement Flash and Latex for that. For example, on our Cray machine, lib size really probably we should use. So there may be or there be some 1 or 2 libraries that are contained in MKL, for example, faster than lib size, but in general, on the Cray machine, you want to use Cray lib size because Cray has optimized that. Similarly, for different machines, for example, for Nautilus, for example, MKL is the best. You probably don't want to use HML on that machine. So, although this kind of different vendor libraries are provided, but there you can try to optimize it. We've got to support different Flash Latex, Nautilus also support different things. And here's just a quick slide on what Cray lib size provides on our machines, and it has Flash Latex FFT, it also has Flux and Latex that provides FFPW. So Cray has done all this work to tune it to their machines, and it also has its own FFT, and which FFPW provided by Cray or Cray FFT. It's a different thing, so maybe see which one performs better. MKL is also available on our machines and it also provides this kind of autism person. I think that, and I'll be happy to answer any question if I can.
Yes, you said some, was that using the 2002 to the system?
I don't know the yeah. So MFW is written in C. But a lot of people have used it before the 2002. But now with the latest version, it's really used the 2002 so that you can use things like FMCW and in cases, probably even in most cases, you can allocate with Fortran allocate and use exactly that would to improve the best performance. That's argument from FMCW. So not to say that you have to use the 2000 syntax to use it.